I kind of goofed and I wrote it twice. So what this should say is like you just cross out this here. Anyways, so here solid iron 3 oxide and carbon dioxide gas produce iron metal and carbon dioxide gas. Okay. So solid iron 3 oxide, well iron is Fe. Now the 3 is not saying that we have 3 irons. It's saying that each iron is a +3 charge. Because iron's a transition metal, sometimes iron could be a +2 charge. Oxygen is a -2 charge. Charge has got to go to 0. 3 minus 2 doesn't equal 0. To get them to cancel out, cross the charges. Meaning the charge on oxygen is how many irons you need. The charge on iron is how many oxygens you need. So it'd be Fe2O3. But you also need to include the state of matter. So the state of matter here, they say is solid, so you'd put an S. Okay? And then plus carbon monoxide gas. So CO, and you're going to put a G there. Okay? And then that's going to produce iron metal, so Fe. And metal is solid, right? Because swords. All right? And that makes carbon dioxide gas, so carbon dioxide di is 2. G, so you put a G. And there you go. Now, what you're going to do later on today, like when you're doing some of the post-lab questions, is you're going to end up balancing the equation after you write it. I didn't have you do it in the warm-up, but that's something you're going to incorporate today as well. So keep that in mind for when you're doing some of the questions of the formative. Going to the second question, you have sulfuric acid and sodium hydroxide react to form, so that's like your arrow, sodium sulfate, and water. So my reactants would be sulfuric acid. So sulfuric acid, that's referring to the sulfate ion, which is SO4. It's got a -2 charge. Acids always have the hydrogen in front of it. So here you'd have a hydrogen, but hydrogen's a +1 charge. So I'm going to need 2 hydrogens. It's H2SO4. And then acids are always aqueous, always AQ. Acids are something that's dissolved in water. And sodium hydroxide, so plus sodium hydroxide. Sodium is Na, hydroxide is OH. Sodium's a +1 charge, hydroxide's a -1. Charge has got to go to 0, and they're already balanced. Now, what would be the state of matter of sodium hydroxide? How would you know? And say it. It would be a solid. So ionic compounds assume they're a solid unless they say otherwise. Now in today's lab, when you're going to write out the chemical formulas, you're going to work with 2 ionic compounds, but they're actually aqueous. So like AgNO3 and calcium chloride, those are both going to be aqueous. So keep that in mind. In other words, I'm not telling you the states of matter during the lab because you're able to observe that with your eyes. But on the warm-up, if they don't say anything, you assume it's a solid. All right, and reacts to form sodium sulfate. So sodium is Na, sulfate is SO4. Sulfate's got a -2 charge. Sodium has a +1, so we're going to need 2 sodium. So it's Na2SO4, and then they don't say the state of matter. Bless you. So you assume it's a solid. And water. What is the state of matter of water? Yeah, water is always a liquid, unless they say like water vapor or something like that. So then that would be your answer. Later on today, I'm going to have you again balance the equations whenever you're filling out the rest of the formative. But here, I just want to leave it just as that. Okay? All right. Hopping into our notes, the first kind of reaction we have is a synthesis reaction. So in a synthesis reaction, what you're doing is you're going to take 2 separate things, or it could be multiple separate things. So another way to think of this is you have more reactant, and then you make fewer products. So in this case, you had 2 reactants, and you end up making 1 product. That would be called a synthesis reaction. So the general format would be A plus B gives you AB. So here you have two reactants and you only make one product. An example with elements would be carbon plus oxygen makes carbon dioxide. Here, if we look at it with like compounds, you'd have like calcium oxide plus water gives you calcium hydroxide. So again, two separate elements, or in this case compounds, make one compound. Okay? I'll leave you a second to finish writing. All right. Second reaction is decomposition reaction. So in a decomposition reaction, it's the opposite of a synthesis reaction. Here, you have fewer reactants, or in this case, you just have one reactant, and then you make more products than you had reactants. So here, this one reactant breaks apart into two separate products. And the general format would be AB breaks apart into A plus B. Okay. Look at it with elements. Here you'd have like carbon monoxide. That breaks apart into the carbon and the oxygen. Those two elements. Or if you look at it with compounds, you have one compound, the calcium hydroxide. That breaks apart into calcium oxide plus water. So I think there's some amount of common sense with this, but you're just looking for the pattern there. Give you a second to finish writing. All right, moving on. A combustion reaction. Now we've talked about a combustion reaction before. So in a combustion reaction, you're taking some sort of fuel source. Typically that fuel source is what we call a hydrocarbon. A hydrocarbon, an example that they're using here would be CH4. Hydrocarbon is something that's carbon with hydrogen. Now, actually in the lab today, the combustion reaction you're doing isn't with a hydrocarbon. Not all combustion reactions have to be a hydrocarbon, but the most common types would be with a hydrocarbon. Anyways, you know it's a combustion reaction when you combine some sort of fuel source with oxygen and then you produce carbon dioxide and water. So if you're looking at a chemical reaction and you see oxygen and you make carbon dioxide and water, it's got to be all three of those, oxygen, carbon dioxide, water, you know it's a combustion reaction. And remember when you're balancing these, what was the kind of thing I gave you to remember for how you balance those? CHO? Yeah. You go CHO, so CHO. So balance the carbon first, then the hydrogen, then the oxygen. All right. Looking at the, this is fourth kind of reaction, double replacement reaction. Now the name, also called double displacement, sometimes you'll see. Like in your lab, I think you use the word displacement, replacement, displacement. It's the same idea. Here the idea is, and to understand this, you have to remember about cations and anions. So remember cations, the T in cation looks like a positive sign. Cations are positive. Anions, we said, are things that give you a negative charge. What are typically our cations? I got a graph table. Remember? The cations are typically our metals, and the anions are typically your nonmetals. Okay, so looking at the format, it'd be AB plus CD gives you AD plus CB. So here's kind of the format. A would be my cation. C would be my anion. So when they come together, or let me go over to CD. C would be your cation, D would be your anion. So what's happening is you're swapping positions. B and D are going to swap with each other. So now the cation A is going with the anion D, and the cation C is pairing up with the anion B. Okay? So looking at our example, silver nitrate plus sodium chloride gives you silver chloride plus sodium nitrate. So here, silver would be my cation, nitrate's my anion, sodium's my cation, chlorine's my anion. So they're going to swap positions. They're going to double displacement. Two things are switching positions. So the chlorine and the nitrate are going to swap positions. So now you get silver chloride and sodium nitrate. Okay? They're like swap and dance partners. Okay. Let me get this erased here. All right, the last kind is called a single replacement reaction. So, or sometimes called a single displacement reaction. So, in a single displacement reaction, there's only one thing switching position. That's why it's a single replacement. Now, here's the format you'll see. If you see an element plus a compound, and then you create, on the other side, you have then a compound plus an element. That's a sign it's a single replacement reaction. Okay? Actually, if you go back to your last slide, I want to add something to it. Using that same format, double displacement is a compound plus a compound, and then you create two compounds. Compound, and then you just say swap positions to make two new compounds. So going back to the single replacement, the only difference is you're starting with an element and a compound, and you make a compound and an element. So the general formula would be A plus BC gives you AC plus B. So what's happening here is A is swapping positions with B. A is basically A is Mr. Steelio Girl coming in and kicking out B. B's by himself, if you will. Okay. If we look here, two examples. You got potassium plus sodium chloride gives you KCl plus Na. So here, well, let me ask you this. Let's say you didn't see these products. Those products were covered up. How would you know that K, like as they're showing it, they're showing that K is swapping positions with Na. Why is K not swapping positions with Cl? In other words, why aren't we making like KNA plus Cl2? Why isn't it that? Okay. Yes, yeah. So you're swapping potassium here is a cation. It makes that positive charge. Sodium is also a cation, so they swap with each other. That way you have your new compound is still a cation plus an anion, and then you have the other cation left by itself. Okay? You can't have just two metals coming together like that. So let's look at the second example. Here you have chlorine plus plus sodium bromide makes sodium chloride plus bromide, or bromine gas. Now, same question, why wouldn't it be, here they're showing that the Cl and the Br are swapping positions. Well, why can't Cl and Na swap positions? Why couldn't it be, ClBr plus Na. And it's really important you understand that, like why it couldn't be that. Thoughts? The reason why is Cl is an anion. It makes a negative charge. So is bromine. So the anions have to swap spots. Na is a cation. They can't swap positions. Then you would have two anions together. So then now you then get cation, anion, and then the other anion, bromine, is left by itself. Any questions about any of that? All right, so let me stop the recording.